Next, we're going to cover a topic that's near and dear to my heart, collaborative filtering. And if you've ever been to someplace like Amazon.com and see something like people who bought this also bought, or similar movies on IMDb.com, I used to work on that. And I'm going to show you some general algorithms on how that works under the hood. Now, I can't tell you exactly how Amazon does it because Jeff Bezos would hunt me down and probably do terrible things to me. But I can tell you some generally known techniques that you can build upon for doing something similar. So let's talk about a technique called item-based collaborative filtering and how that works. And we'll apply it to our movie lens data to actually figure out similar movies to each other based on user ratings. Let's see how that works. Okay, we did breadth first search and degrees of separation. Now we're going to do collaborative filtering, actually finding similar movies, just looking at movie ratings data. So we're doing some pretty complicated and advanced stuff here at this point. And the good news is this is probably the culmination of the course in terms of difficulty level. Stay with me, bear with me, because after this lecture, things get easier. Trust me. Mainly, again, I just want to make sure that you understand that complex problems that may not appear to be a Spark problem can be framed as Spark problems. So this is yet another example of taking something that you might not think of as being distributable and actually making it into something that you can run on Spark with massive data sets. Now, in addition to talking about finding similar movies using the Movie Lens ratings data set, we're also going to introduce a concept called caching and persisting RDDs, which is very important to know as well. Okay, so we're going to find similar movies to each other based on movie ratings, and Movie Lens does this for you under the hood. It can actually find movies that are similar to each other, and it uses that to power its recommendations. And this is also, something you see on websites all over the place. Amazon does this stuff. IMDb does this stuff. Like I said, they all have their own little secret sauce on how they do it. Netflix does it too. So this is just one way that I'm going to show you right now. So how does item-based collaborative filtering work? Well, here's how we're going to do it. And it's only one way to do it. There are many techniques. This is just one that's easier to explain. So what we do is we find every pair of movies that were watched by the same person, okay? And then we find all the users that watched that pair of movies and compare how similar their ratings were for each one. So the idea is that if you have, two movies that were watched by a bunch of people and they all rated them similarly, those movies are probably similar to each other in some way, shape, or form. So after we do that, we can then compute the similarity of each movie pair, sort them by the movie, and then by the strength of similarities. And then you can slice and dice the results and look up a specific movie and find the movies that are most similar to it. Okay, so again, that's just one way to do it. Makes a little bit more sense with an illustration. So let's imagine that this good-looking little clip art woman watched Star Wars and Star Wars: The Empire Strikes Back and rated them both similarly. And Mr. clip art Mohawk guy here comes along and also rates both movies and rates them in a similar way to the first person did. So with that information, we can establish a connection between these two movies, and we know that there is some relationship between those two. So Mr. Handlebar Mustache comes along, and he lives in some strange world where he's never seen the first Star Wars movie, but he has seen The Empire Strikes Back. So what we could do at this point, if we were creating movie recommendations, would be to take the fact that we discovered a connection between The Empire Strikes Back and Star Wars based on these other ratings, and then we can say, hey, here's another movie you might be interested in. Star Wars, it turns out, is somehow connected to The Empire Strikes Back, so maybe you should check that out too. So that's it in a nutshell. That's item-based collaborative filtering. Pretty simple concept, fancy name, right? That tends to be the case in machine learning and data mining, actually. You hear a lot of big fancy words and terms that sound very highfalutin and academic, but when it comes down to it, the concepts aren't that complicated. However, turning this into a Spark program is complicated. And I'm just going to kind of walk you through the approach that I used here. Again, the point here is just to illustrate how you can take something like this and turn it into a Spark problem. It's just an example to look at. So if you don't totally get everything that's going on here, that's okay. Important thing is that you see that you can take a complex problem like this and make a Spark problem out of it and make it actually work. So here's our strategy. And what we're going to do is map the set of input ratings from the Movie Lens data set to key value pairs where the key is the user ID and the value is this composite movie ID and rating structure. Okay, so for every line of input, we're going to create a key value where the key is the user and the value is the rating for a given movie ID. Now next we need to find every movie pair that was rated by the same users. Okay, and to do that, while ago, I talked about some operations you can do on key value RDDs that were very SQL-ish, and one of them was a join operation. And it turns out if you join a database with itself, you end up getting every possible permutation within that database. So by doing a self-join, basically joining that RDD with itself, I'll get back every single possible pair of movies that were rated by that same movie. So what I end up with here is this huge list, because this blows up quickly. It's like, a Cartesian combination, right? We're going to have this huge list of user IDs followed by every possible pair of movies that they watched together. So we'll have a user ID watched this movie and rated it something, and they also watched this other movie and rated it something. And we will get that for every combination of movies that they had watched, okay? Now we're going to get some duplicate pairs as part of that process. We're going to get some things that are in different orders, or maybe we'll get the same movie in movie ID 1 and the same movie in movie ID 2. We're going to strip out all that duplicate, redundant information just to boil things down a little bit more, okay? Now, next, we're going to make the movie pairs the key, because what we really care about is the similarity strength between pairs of movies, okay? That's the end goal here. So we're going to shuffle this data around, and we're going to map this data so that it looks like movie ID 1, movie ID 2, this composite value ends up being the key, and the value ends up being the ratings of those two movies. So we can say movie ID 1 and movie ID 2 were watched together by some person and rated with these two values. Okay, at this point, the user ID is irrelevant. We don't really care who the individual was. All we care about is that some person watched these movies together and gave them these ratings. Okay, with me so far? Next, we're going to do a group by key. So we want to combine together all the ratings that individuals made for that given pair of movies. All right, with me so far? So what we had before this point was for every individual movie pair that was watched by a given user, what that user rated each one. And now we're going to combine together all of the ratings that were made for that movie pair across the entire data set. And once we have all that together, we can compute the similarity between those two movies just by looking at the similarity between the sets of ratings that different users gave to that movie. Okay? And there are many ways to compute similarity. We'll pick one that's easy to do. And now we have what we need. We just need to sort, save, and display the results. So let's go off and look at the code and make it actually happen. So one thing I want to point out first too is that we're doing some pretty heavy lifting here. That self-join is a huge operation. It generates a huge RDD. So it's time to start splitting this up across more than just one CPU. Odds are your PC at home has at least 2 cores on it. So by doing this one little trick here, instead of just saying setMaster local, we're going to do setMaster local open bracket star close bracket. And that syntax means go take advantage of every core you have available on this computer and run a separate executor. So for the first time, we're going to be running a Spark program across multiple executors. It will still be on just on your computer, but we're actually going to be running as many executors as you have cores and combining the results back together later on. So again, let's go take a look. One other thing I want to mention too is caching RDDs, and I'll point this out as we go through the code. Now, we're actually going to compute the RDD of movie similarities, and we're going to look at it a couple of times. And the way Spark works, as soon as you call an action, it just discards that RDD. So if you actually want to use an RDD more than once and perform more than one action on it, you need to tell Spark explicitly to cache it and make it persistent. Otherwise, Spark might have to go back and reconstruct that RDD all over again, and you might end up, doubling the amount of work that you have to do. That would be bad, because that join operation, that self-join, is very expensive in this example, and we don't want to have to do that twice. Okay? So what we'll do instead is once we have that RDD of movie similarities, we're going to call cache on it or persist in order to keep it around and prevent the need from recomputing it again. What's the difference between cache and persist? They're actually very similar. The only real difference is that persist gives you an optional argument that lets you cache it to disk instead of just memory. So if you're really paranoid about losing that RDD and you don't want to lose it even if a node fails, you can use persist to make sure that it writes it to disk. Obviously, that's going to take more time and consume disk space, whereas cache will not. Now, let's really go look at the code and run this beast. So there you have the concepts behind item-based collaborative filtering. It's a fancy word, but it's a pretty simple concept, right? So let's figure out how to take that and turn it into a Spark problem. So again, this is an example of taking a more complex business problem and trying to frame it as a Spark problem that can be horizontally partitioned on a Spark cluster so you can take massive amounts of ratings data and process them still with good results. So let's dive in next and turn this into some code.